before I introduce Scott, I just want to remind everybody what the TRA stands for. It's the Retiree Association. It's open to all Northrop Grumman and TRW legacy retirees. So we have, right now, we're up to 161 and more, and up to 250 people joining in. And I'd like to really invite all of you who aren't members of TRA to look at our website and get familiar with us. It's at www.tra-spacecraft.org. And it's a really good source to keep in touch with people, news. We have newsletters and everything. And we've had, last year, we've been able to keep in touch with a lot of people due to the pandemic with our directory and our emails and our Facebook page. So I'd like to invite you all to join if you haven't.
Hey, Marianne.
Yeah.
That URL was TRA-spacepark.org.
Oh, I'm sorry. I guess I have spacecraft on the brain.
You're an old spacecraft person. So.
What it gets for being a former spacecraft manager, huh?
Yeah.
Yeah. Well, I'm just all excited about James Webb. I just think spacecraft, right? Yeah. So, well, anyway, so let's get on with the show today. It's a great thing. We're all looking forward to things in 2021. And today you'll know what to really look forward to by hearing Scott. Scott is, I think a lot of you know Scott. He's currently Vice President and Program Manager for James Webb Space Telescope. He was hired into TRW in July 1989. He came from Lehigh University with a BSEE. He started off, like many of you, in system engineering. He completed at USC a fellowship, and he got an MSEE in communication systems. He worked on many programs, including VISIT, MILSTAR, MAPSTAR, Astrolink, AEHF. He was in a variety of roles spanning all aspects: system engineering, integration and test, antennas, program management. A lot of you know him when he ran the big functional area for production control and integration and test. And since after running a classified program for about a year, he's been our program manager, the Northrop Grumman program manager for Webb since 2009. And without further ado, I'd like to introduce Scott, and he's going to make us really look forward to something in 2021 here, other than COVID. Okay, go ahead, Scott. Welcome.
Thank you, Marianne and Reggie. And every once in a while, you can turn your mics on and laugh, because I'm used to a little bit of feedback in an audience. I prefer to be interactive. At least I see Dina smiling, so that's good, because I'll make jokes. And this is a tough world. I'm a very personable person. When I got to meet this group in the cafeteria, you know, it was really my pleasure to be able to do that. But I've been talking a lot on Zoom for the last year. So I think this will go best. I'll talk through the charts that I have. I don't want to PowerPoint you, but I think you'll find them exciting, because I got some pictures of the hardware. I'll hit some of the questions that people already asked during the presentation, and I'll look at my iPhone and try and go through some more, probably miss some. And then I have time after. I always try and be, respectful of the time that people signed up, for this, for an hour. I guarantee this is going to go over an hour. I will be available for a while after that, but certainly will not take offense, people signing off. So that chance then, as it gets to a smaller crowd and to interact. But let me just start with one amazing acknowledgement, right, for this association. What I'm going to talk about is a product of everybody's work, from legacy TRW and all the other parts, because there's nothing like this that could have been done without standing on the shoulders of what we had done before. And in science alone, Chandra X-ray Observatory and Compton Gamma Ray Observatory, right? Legacy TRW had 2 of the 4 great observatories. NASA, they don't use that terminology anymore, but if they did, Webb would be the 5th, the other 2 being Spitzer and Hubble. But, so we had half of the first 4, really. We got 3/5 of what we'll all call the great observatory. So it's an incredible legacy. But of course, all of this is born on our legacy of everything else we did, many things we can't talk about. And I always like to tell folks, the great thing about Webb is it's the thing you can talk about and be proud of your company and your heritage. And then you can always look at those people and say, and I did something, harder, or, that fed that, so it is the most public thing that we really can talk about. With that means it's the most public thing that can get criticized in the press, as we kind of live and open to the world as we've gone through. And you know, I'm not embarrassed about the bumps we had in the road. I always tell my team, if this came without failure, then we didn't shoot high enough. We didn't try something hard enough. So I think it's really just emblematic that we're pushing the edge so far with Webb, but we're there. And I hope people can get a chance to get to the window. So I'll talk about that a little. I also have a lot of bosses, former bosses on this line there. If you like what I say, you can submit a supplemental to my current boss, Tom Wilson. I'm sure he'd be happy to hear how great a job Scott's doing. But with that, I'm going to share my screen. And this presentation is called By the Numbers. I have a few of them. So I'm going to throw a number up, and usually I can get a little interactive with the audience. But in this one, I'll just tell you what that number means. And the first one of 13,500,000,000 is a rather big number. And of course, most of the audience raised their hand and says, how much it cost? No, that's not how much it costs. We're close. You can ask me that at the end. But 13,500,000,000 is how far back in time this telescope is going to see, which is just, it's mind blowing. And what that means is we're going to see the light that came out of a star that is so far away from us that at the speed of light, it took 13,500,000,000 years for that photon to finally reach our telescope and hit that optic. And we collect it. We're collecting this with a giant optic, 7 times the optic of Hubble. And the importance of that time, that 13.5 billion years, first of all, in round numbers, the universe is 13.7 billion years old. So we're not seeing, call it to that beginning. That's the cosmic dark ages after that. And there was the cosmic microwave background radiation that we used to age the universe, and that Dr. John Mather, our chief scientist on Webb, got a Nobel Prize for. But what we're seeing is the first stars and galaxies that formed. We were, call it fortunate enough. What happened was that at the Big Bang, after some time, all we had was neutral hydrogen and helium. And I love to joke with the kids, if you were only 13.5 billion years old, chemistry would be easy. It'd be your favorite class because you'd only have to memorize element 1 and 2 on the periodic table. There's a little bit of lithium in there, element 3. So imagine that, that's all we had. From that, a fusion reactor, a star formed by hydrogen and helium, and it burnt that hydrogen and helium as a fuel, but burning it in fusion meant it added them together. And it created elements all the way up to iron. And I mean, it's amazing, right? This fusion reactor is creating carbon and all of these elements. And then eventually supernovas with more heat and more mass explode and create the higher elements like gold and platinum and the higher metals. So what we're seeing is chemistry created. We haven't seen that epoch. Hubble's eyeball can't see that far back in time because it can't see as far into the infrared spectrum. I think I'll talk about that a little bit later. So we're building this amazing machine to see the beginning of that. The other thing that we're going to be able to do with not just those old stars and then the planet formations is we're going to see new planets. So then come forward. When we started this project, I forget how many, it may have been like 3 or 0, whatever, confirmed planets. We were sitting there our whole lives living in 9 planets and arguing about Pluto, right? Then we were down to 8. But it turns out every star we believe that you can see in the night sky has a planet around it. It's literally that high. It's in the 90% that if we can look, we can detect a body going around it. But what do we know about those bodies? We only know now when we find them what their rate is, how far away they are from their star, how far they go around, and their mass, but we don't know that they have an atmosphere. And one of the questions that was asked was, can we do that type of mission in terms of understanding life on other planets? And the answer is yes, because any sunlight that goes past that planet but very close to its surface through its atmosphere will leave behind the absorption of any elements in that atmosphere. So when we pick up that fingerprint, we know what the pristine light looks like, and then the filtered light. And if you look in the filtered light, you will be able to tell if that atmosphere has water or carbon dioxide or methane or things that we believe to be signs of at least life as we know it. So Webb will be able to look at these planets, TRAPPIST-1, that was one of the questions in particular, and stare at those and say, not only is it an Earth-like planet, not too hot, not too cold, you know, in terms of how close it is to the sun, but does it have an atmosphere in it that if there was life, you know, life could either have started or lived? And it's unbelievable. That's what this mission will do. I'll give some more technical fun facts. One of the things we have to do in order to perform this mission, 1,500,000 is an interesting number. And that's how far away we have to send this mission in orbit. For those of us like me who spent a long time working on geosynchronous satellites, going up there and doing communications 22,000 miles away, or for those, you know, folks on this room who spent time working, you know, in the Apollo program and things to the moon, that's only 250,000 miles away. I'm converted to miles now, you know, 380 something thousand kilometers. We're going 4 times further than the moon, out to what's called Lagrange point 2. And why are we doing that? We're doing that to enable a mission that needs to operate cold. That's a hint. I'm going to give you another number in the future. We have to see infrared light, and infrared light is also where heat is. So if we don't get cold enough, and that's part of the complexity with Hubble. Hubble is closer to us than San Francisco is when it goes overhead. Hubble's 250, 300 miles, right? In this lower Earth orbit, like the space station. We are going to be 1 million miles away. You know, Hubble has got Earth as this IR source that it's close to. We go away and then we block the sun forever. We can see every star in the universe out there at L2 except our own. The only star we won't look at is our sun. So we'll be able to, you know, again, peer around. So we go 1.5 million miles away from Earth. 10 plus is the plus is the favorite of mine to add on there. This chart's a little bit old in timing, but we designed for a mission life of 10 years. Now, Hubble's been up there 30, but Hubble got serviced 5 times by the space shuttle. That was the advantage of being in low Earth orbit, not only repaired, but improved, you know, with solar array replacements and instruments that got upgraded. We will be overlapping with Hubble, which is an exciting thing. So the fact that they can look at an image with Hubble and what it does more in the optical, little UV, little IR and Webb, and its near and mid infrared, you know, spectrum will be absolutely like stereoscopic, you know, looking at things. So Webb goes up there and we're going to last 10 years. And then as that's happening, other technologies are going to be looking at like star shades and bigger optics. This is a good time to say, I had the opportunity on Wednesday to actually talk to the current acting administrator for NASA, Steve Jerzik. He was here in Redondo Beach in our plant looking at Webb with Senator Moran from Kansas. And then the next day they got to see Perseverance, you know, landing, which was incredibly exciting. They got to see 2 great things. They got to see Webb and they got to see Perseverance. And in talking, you know, with Steve and in particular with the senator about what Webb is going to do, I described it as basically the next set of shoulders. For 50 years, for decades, as we started sending optics into space, take Hubble, it's a single piece of glass, you know, slightly taller than me, a 2.4 meter optic. That's all we've done. Webb is a segmented mirror that can be deployed on orbit, that can be adapted on orbit, and it's 7 times bigger than Hubble. So we didn't just make Hubble a little better. We created an entire new architecture scaled that is now scalable. You could, you know, think of how you could add more segments and build even a bigger mirror. So we really have broke all of the, you know, we talk about being a successor to Hubble, but we're really the next set of shoulders that will last decades, right? And in new space telescopes. So I kind of show a flagship class after us with a star shade. The other cool thing that's on here, TESS as a planet finder, that's a part of our company now. That was built by the Legacy Orbital ATK organization, so now part of Northrop Grumman, and that's a planet finder out there, finding basically things that Webb will look at. So you got all those missions, and I like this chart because I'll talk to the students. Some of them will say, oh my gosh, if you already did Webb, what am I going to do? And they don't realize that every time we do something hard, you know, we get a set of requirements to do something harder, right, to build on that. So I explain how this is a continuum. But we have a 10-year mission life, and Webb will go beyond that, not tremendously beyond that because we're not serviceable. Effectively, our life limiter is predicted to be running out of fuel for station keeping. You know, we do need fuel to do momentum offloading and station keeping in addition to safe mode. Here's the two numbers that kind of bookend us, and I'll just jump to it. I talked about temperatures. The Webb telescope to see infrared, our optics will run at near minus 400 degrees Fahrenheit, minus 388. That's only 38 degrees above zero in the Kelvin scale, where molecules stop moving. Somebody asked that question, what will the optic run at? And that's about what it is. And we have to be that cold, again, otherwise we'll only see ourselves. We won't find a photon that took its 13.5 billion years to get to us. We'll only see ourselves. So we have to be super cold, which is an incredible technological challenge. We had to, develop or qualify glues and composite materials and things, that can work stably, because it needs to point at there. And then part of it is this giant sun shield. The two most, eye-watering things when you look at Webb are the big gold optic and the tennis court-sized sun shield. And that sun shield, out of 5 layers of Kapton, I'd be happy to talk more, effectively blocks plus 185 degrees Fahrenheit coming in from the sunny side, kicks out, that along with other things in the design. It basically reflects or vents out heat and eventually gets down to minus 388. That 600 degree differential, if you had to go buy that as sunscreen in the store, would be around 1.2 million SPF at CVS. So you can't just go buy this. You need Tier W Northrop engineers to build it for you. So we got this huge, thing that has to be hot on one side and cold on the other. These two numbers are often the answer as to, Scott, what keeps you up at night? What's the most challenging thing in Webb? What do you worry about the most? And that's 40 and 178. So what this graphic shows from left to right is we start folded in a 5-meter fairing, but we're a 6.5 meter optic. So we're bigger. We have a sun shield, right? I told you it's the size of a tennis court, right? That fits in a 5-meter fairing because it's folded up like a parachute. And then all of those stages, as it opens this way and this way and this way and tightens up, and then mirrors open, and then the secondary mirror comes out. All of that starts, though, being assembled and attached and bolted to each other with 178 release devices and 40 deployable structures. I give that in, reverse order there. So 40 things that have to move on orbit and 178 things that start by holding it out, non-explosive actuators, that when we send the command, the split spool nut has to open up, let the bolt come out, and then let something move to a final position. Those are also known as single point failures. As impressive and absolutely impressive Perseverance landing is, and Curiosity's was back in 2012, when I met the mission manager for Curiosity, who was on a review panel for Webb, he goes, oh, Curiosity had about 75 single point failures. Webb has 340 something single point failures. So the complexity, again, of what we're doing is pushed every single envelope of what you could imagine. So those things open there. So now let me show you some pictures about a half hour in, and then, I really want to get to questions and then interaction, but it was an incredible year in 21. Now I'm telling a story that, Dave Shuckstis and maybe Martin are on it, and C. Mohan and many others that had such a big part to do in Webb. Maybe they're getting teary-eyed looking at this if they haven't been. This is the fully deployed mirror, and that's a human. That we didn't pick our smallest human. That's a reasonably sized human standing on that diving board to the right of it. The mirror is 22 feet in diameter, when the way you want to look at it. It's 18 beryllium mirror segments polished for 8 years. Thank you, Martin, for getting the mirrors mostly done by the time I took over. 8 years to make mirrors, from grounding up, beryllium into powder, to forging it into a blank, to machining it coarsely, to polishing it. And at the very end of each of those mirrors, they were scraping an atom off the surface. The surface of those mirrors is so accurate that the largest error is in nanometers. It's on the order of the size of bacteria. And somebody once did the math at, what if our job was to flatten out? I mean, they're not flat, they have their concave shape, but basically to create a smooth surface of the United States, from California to New Jersey, 2,500 miles. The equivalent bump, where there used to be Rocky Mountains or Grand Canyons, could only be a few inches tall. on 2,500 miles. When you're only 1.5 meter flat to flat, that means you have 20 nanometers of error on that. That's how accurate, because basically any bumps on the mirror would cause the photon to dash off in a direction that we don't want it, because we have to not only bounce it off the primary mirror, then a secondary mirror, then a tertiary mirror, and then some fine steering mirrors. We got to bounce that photon into that nose. That black nose that's sticking out is the optical bench that then sends the photons to 4 instruments that do the science. So that's our deployed mirror. That was just in March. I mean, I just stood at the window and stared at that, for hours. And then we stowed everything up, and this is looking kind of head on. So if we were going into the payload fairing, that's as wide, and you see what are incredibly courageous and skilled workers, one of them lying down on the belly on the left side on the diving board, and one on the knees on the right side as they were looking at as we assemble. So when Webb is only folded up, it's less than 16 feet across. It's about 40 feet high. And then it's packaged with the sun shield and a parachute, and the mirrors are folded on its side. And this was the configuration that we put it in for launch, because after this, we had to send it to acoustics and vibration testing to simulate that violent rocket ride. We had done that prior with the spacecraft and the sun shield and with the optics and the instruments, but then we had to do it together as an observatory, a top assembly. This is the other side of that, though. After we had stowed that was actually to get us, prepped to make sure we knew. But then we had to do one last thing where we had to open up again to do some things where we affixed the final fasteners in the center. But this gave us this cool view through the goalpost there, through what are called the spreader bars that hold the sun shield as it stacks. This gives you that front end view of the mirror when stowed. So that's a mirror that fits in a 5-meter fairing, right? It's got 2 wings of 3 mirrors that are folded back like ears on the side. In July, we are doing comprehensive system tests. And then in August, ground segment tests. It's hard to show off the electrical people on this program. I'm an electrical engineer, but we just end up being 1s and 0s or RF wavelengths. So there's a person working around a harness. but we did a lot of electrical testing on this, an incredible amount. And that testing was done right smack in COVID. I mean, when we were doing that, we had to put up new work stands and space out control centers that would have 30, 40 people in it, and cut that in less than half, and then put people in remote and, on headsets, which you lose, right? You lose the ability for engineers to look at each other, look at facial expressions and ask questions. But that team hit it like money, right? They did the comprehensive system and the ground test, spot on. Then we went to environmental test and come back. There, if you look, there's a bunch of smiling faces inside their masks. So that's the stowed vehicle from the front side. So the composite structure with the pink MLI that you see blocking the mirror is the folded up structure that holds the sun shield. And again, that's what it takes to fit in a 5-meter fairing. There's a great group shot of the people. This is right as we got back in our high bay from environmental testing. The one thing about Webb is we were practicing wearing masks for a long time before COVID. So we had very well trained folks. I mean, they're in their masks, hoods, gloves, tape. This is a 10,000 class clean room, that we're working on. I kind of joked on Millstar and Advanced CHF. I think before they went up, Reggie went out there with like a little rag and wiped it down, and it was good enough. Launched that ComSat. We'll still pick up 40 gigahertz signals, but for this one, we got to keep every speck of dust off of it. Just miraculous to get that back. And then this, December of 2020, we deployed the sun shield. This was the 3rd time we had deployed it on the ground, and the last time we'll deploy it on the ground. The next and the 4th deployment will be on orbit, and that is arguably one of the most complicated things we do. Heavily complicated by doing it in gravity, right? This is designed to work in 0G. So that is a 5-layer sun shield deployed and tensioned in December, and we got that in right before the holiday break, and was able to give the team off the whole holiday break. And before that, we were going to have to work like 4 days between Christmas and New Year's. I mean, the team really crushed it. What a reward to see that deployed. just before the end of the year. And that was proof that we survived the rocket ride, acoustics and vibe. And we learned things. We still had some tremendous lessons learned, but they'll give us that last and finest improvement. So when we package it, when we put it together, when we fasten it, but it's really, it's an artisan thing, whatever term you want to use for craftsmanship, to fold membranes and tuck them in and put the fasteners in. It isn't just serrated plates or hinges or bolts getting, literally the tucking of those membranes in. So that is a tremendous amount of work that has been done by this team since a victory in 2002 of the James Webb Space Telescope. For all you alumni and alumni in the company, that you're staring at, the proof that this is going to work. So I didn't put in here, what do we got left? Probably stare at this picture. Let me just talk to that briefly, because I think the next thing was Q&A. What we got is still a lot of work in front of us. And it's also hard because in COVID, we're working around how many shifts we can get in and some limitations. But we're set to launch on Halloween, October 31st. And it is a real date. We have margin to make it. It's the date we set in 2018, close. We set early 21, but COVID moved us out to October 21. But to me, it's the same plan. COVID's a mulligan for us. Our performance was just outstanding for the last 3 years. So we still have to stow the sun shield. We have to do the deployments of those wings. We haven't done those after environmental tests yet. So we do have some more deployments left. And we just finished our comprehensive system test 5. We have a Delta test to do. We have another ground segment test. So basically between now and June and July, we've got some more subsystem testing, but a few more deployments, and then it's folding. It's just putting this thing back together, as you saw in one of the other pictures. We put this one into a boat. People asked, why a boat? I'll explain that in a second, but we go in a boat out of one of the Navy ports, Long Beach or Seal Beach. And we go through the Panama Canal and we bring this to French Guiana, and we launch this on an Ariane 5 rocket. That was a rocket selected by NASA as a part of their partnership with the European Space Agency. So this is a Canadian Space Agency, European Space Agency, and NASA are all partnered in Webb, US being certainly the largest part of that. But one of the things they're providing is the rocket. So why a boat? There's a few stories on that. We were set to try, when I came on the program, to go on a C5. We were still talking about that. But what ultimately broke the bank is the mass of Webb, which is 14,400 pounds, wet. So it'll be a little lighter there. The mass of Webb, its container, its environmental controls, and everything that would go across are heavier than the capability of the bridges in French Guiana, from where you land on the skid strip to where you process vehicles on the coast. There's actually 7 or so in-country bridges. The country wasn't going to rebuild all its bridges for us. So we're coming in like the rockets come into French Guiana. They don't get sent on a plane. An Ariane core that's built in Europe comes from Germany on these same boats, right? One of them. It comes beachside and it comes up. So we are coming in on there. It also let us build a little bigger shipping container. Otherwise, we were going to have to knock every corner off of that shipping container to fit in a C5C, the largest transport, where you take the seats out of the back, where you do everything. So Webb is going by boat transport to French Guiana. So our plan is to deliver it in August and spend, a little less than 3 months processing the vehicle down there. We got margin to delivery. We got margin at the launch base, and light that thing and go on October 31st and end up at Lagrange Point 29 days later. 14 days of that are deploying on orbit. So if you watch Perseverance yesterday, and if you watch Curiosity or the replay of it, it was 7 minutes of terror. 7 minutes from when it hits in the atmosphere and it does the aero braking, and then eventually the parachute, and then the retro thrusters, and then the crane deployment. We have 14 days of terror. We are going to sit there and watch things deploy as it's traveling 1 million miles away. And it's going to be exciting. I don't know. We're going to be holding our breath and find times to take breaks, but it'll, be hard. We'll be watching it at and commanding it in Baltimore at the Johns Hopkins campus there, what's called the Space Telescope Science Institute. And they're the same organization that is running Hubble. They actually do the mock now in Goddard, but the SOC out of the Space Telescope Science Institute. So I know Reggie thinks I love talking this long. I do, and I got 10 or 15 more questions, but I think maybe I'll jump back to those, Reggie or Marianne, how you do it. I think it would be good to either hear a voice or have you guys ask me a question or two, and then I'll go some of the pre-printed ones so I could take a sip of iced tea.
This is Steph. I'll go from the previously submitted questions. People are asking about the future capability, if any, to have remote docking capability or to service instruments or replace them or whatever, repair them post-launch. Even though that wasn't in the original set of requirements, was there anything to possibly accommodate?
That's a real tough one, and it came up a couple of times. I can't remember if that came up on Reggie's watch or not, but we have, we're putting fiducials around it, which mean the targets that a remote prox-op, docking thing could go up to us and grab us by the same ring we attach ourselves to the launch vehicle. So we are capable of being grabbed. Now, when you grab Webb, what are you gonna do with it? It's not designed to be serviceable. So we don't have line replaceable units. You cannot take a reaction wheel off of this. You can't take a camera, off an instrument or something like that. So most likely it would be one of two things if that servicing mission even exists, right? Nobody's done a robotic servicing mission at Lagrange Point 2. Northrop has done a mission extension vehicle of a Intelsat, right? We grabbed it from the graveyard orbit up there in SuperSync and Geo and brought it back. But for us, nothing's been done. But if you could, you can maybe use that for a deployment issue. If there was something, that maybe you wanted to shake it, and then possibly a refueling. I wouldn't cut that, out of the possibility that in 10 years, somebody figures out. DARPA's been looking at it, NASA's been looking at it, the Air Force has been looking at, a refueling type thing, but not an improvement, not a change out of a unit.
Well,
Scott, this is Tony Arnott.
Then
Is there going to be a launch party for this thing at the plant?
Yeah, great question, Tony. Hey, Tony, how you doing?
All right, boss. How about you? Long time no see.
Yeah, they will be. I mean, of course, what I can't tell anyone, with specificity is it's what will COVID be like in October, right? It's, so the need to do something around the country, certainly for our Northrop people at sites, what we would do in the S cafeteria and showing the launch and that kind of, and then figuring out how we can connect people into the deployment, right? How do you follow along with, video of what's going on and, the telemetry response. So yes, there will be, hold tight. Sure, we'll let even, everybody know, but especially make sure we let the TRA know. The question will be, how can we get together in October? My hope is, personally, I won't be standing next to you because I do get to go to Kourou. So the current program manager, deputy program manager now, Vince Heeg. So a year ago, Gus Macrianis, he's a retiree. I don't know if you recruited him yet. I got him back on contracting, so he's got enough money if you can, if you need dues. But Gus retired and Vince took over the deputy position. So Vince will start off in the mock in John's, at the Institute. With his counterpart, John Durning, and I will start off in Kourou. So I'll be as a part of the launch in Kourou. And after the launch with Bill Oakes, and then Bill and I will then go to the mock and then stay there for 2 weeks on console as we deploy.
All right, thanks.
Colonel, a question. Given on the assumption that your 200 release devices and separation devices all work based on repeated testing during your environmental testing and what have you, what oversight is Northrop Grumman and NASA putting on the launch vehicle subcontractors to make sure their systems don't just, blow up and they say, oh, well, it's just another problem?
Well, that's a savvy question. It was also one that came up in 2018 by the independent review board led by Tom Young about the certification of it. So NASA through Kennedy oversees the qualification of the launch vehicle. However, it isn't the same as certifying a launch vehicle as we do for a US rocket. And part of that is ITAR and other types of things that are just a natural part. So they have deep understanding of it. I can't, I've been to the launch vehicle meetings. It's not my, certainly my skills. I've been well promoted or beyond my level of competence. Former bosses on here. But the Kennedy Space Center for NASA is in there and looking at things. Certainly where we are closest to was the capability of the rocket, like coupled loads and thermal profile and rolls, and all the Reggie's engineers tirelessly built maybe the most nodal models that I can imagine, right, of something to see how that reacts and then do that. But the vehicle itself and its performance, now Ariane has somewhere on the order of 80, rocket rides on the Ariane 5. There was a concern that we may not launch in time based on our readiness and end up on an Ariane 6. That will not be the case. We will launch on one of the remaining Ariane 5s. So it is a long legacy vehicle, but of course, the nature of how it couples to us is very unique. So it's a Kennedy oversight question. So they are a participant, but it's not the same as certification.
Thank you.
This is
Scott,
Stephanie.
this is
Just
Bob
to,
Kammer. Ask astronomers, what do they want to see first on this thing when it finally starts taking pictures?
A lot. There were over 1,000 proposals for the first year, representing almost 5,000, investigators, and that hasn't been selected yet in terms of that down. I think it may be March, but what has been selected by Webb that made it a little bit more unique, and then I'll give you a little bit more of an answer where I know they're going to look, is what's called early release science. Webb is so complicated with its instruments that they can't wait a normal cycle where you propose and then run a mission, right, for a year. You collect, and then people see that, and then they tune their missions up, and then they propose. But those proposers in year 2 don't get their missions till year 3. On a 10-year mission life, that's prohibitive. So NASA and the science world agree that there's an early release science that has no proprietary. And what I mean by proprietary is a scientist gets used typically 1 year of their own purpose use of science so that they can go win a Nobel Prize. Us engineers, we move on and build something else, but the scientists are trying to get their Nobels. But there's a bunch of science that is going to come out that everybody gets. Probably not the most, very using all the instrument modes. But the first science is a combination of the two things I talked about. It's trying to point it in a place almost like Hubble, where you look where you expect to see the oldest stars, where you're looking for this first star formation 13.5 billion years ago. And then at near, whatever form of how many less, 100 million light year or so, exoplanets to look for signs of life. TRAPPIST-1 system, I imagine, will be in early, because it's already known to have the Goldilocks type of a planet, not too hot, not too cold. But the final answer hasn't been selected yet.
Any leading candidates?
I mean, just the TRAPPIST, I know, is a heavy thing. And then again, things around the first stars. I'll tell you what was really good early on, though, is Webb has science goals across almost everything except for heliophysics, and heliophysics meaning just our star. In Earth, so we won't see a star. But planetary, it will look at, everybody thinks our mission is just going to look at other galaxies, in the universe. It also will be able to look at Mars and Jupiter and, and Saturn and things like that. So, but I'm not, as close to the science. They keep us busy getting the vehicle ready. So to some degree, I'll hear when others hear. Maybe I'll hear the day before, but.
So Scott, I've muted everybody. I wanted to get Stephanie and Pam an opportunity to ask some of the questions that were submitted through chat, and then we'll open this up to a broader discussion in about maybe 10 minutes or so.
Why don't I go ahead and there's a question about whether there is a concern about hurricanes during the time when the ship leaves in August. Scott's muted.
Oh, I have to unmute. There's a concern in general, really any time of the year, about sea state in tropical storms. So we won't leave the dock unless whatever forward-looking predictors are, and it'll be led by also, I don't, again, not my area, there'll be a head boats, right, also that will be measuring sea states, and there'll be a planned course such that if there needs to be, call it a safe port to go into, to weather out a storm. It's a 12-day trip, of which half of that about is in the Panama Canal locks. So it's not, it's not short, where you just kind of buzz through and get there, but it's enough where our weather system should be able to, predict sea states. And then, that may be a pacing item. We may say, let's not, go. I will say a very interesting thing. I can go on different topics, but, when we changed to the boat, it actually helped us in terms of the loads profile, but it changed. So now we have this low cycle load, different than the landing load of a C5 that you have to design for, right? More of a shock and abrupt. So we were able to lightweight the vehicle a little bit more due to taking landing loads out, but then we had to do, Reem Hajal, talk to her, she's a retiree now, about how we looked at the low cycle loads of a boat. But that's what we'll do, we'll look forward.
This Steph, combining questions from Nina Wooden and Bill Stieritz. Can you talk about when the vehicle will actually leave LA, and will there be on-site tours, you think? I mean, who knows, right? But if you can talk about either of those.
So here's where we are now. First of all, when it leaves, I do expect that there will not be a tremendous amount of pomp and circumstance from the standard point of, while this is not a classified vehicle, it is a $9 billion vehicle. And they will not want to have, a big to-do around that, and just in terms of, control and concern. That being said, I don't know how secretive it can be, that. But all that being said, right now, the viewing window is open. Reggie's a tour guide, and I think we'll say they're sold out. I think we're looking to even put more times to get more tour guides. The limitation at the window is 7 people, so you can only bring so many people in to be, safe and socially distanced. And there's 2 viewing windows. There's a high and a low for those who haven't been there. But if you have, it's exciting to look at it from above and look up the optics. So anybody on here, I'm sure, have plenty of friends with a badge. So I would reach out to them and on a Saturday or after work, say, hey, I'm gonna meet you at 6 o'clock. You're gonna take me in the window to see Webb, because it looks really cool now. It'll look different, between now and August, and then eventually it'll end up in a container. But I'll say between now and June, it'll look like some part of, those pictures I showed you. Right now, the sun shield's pulled up on either side as we're getting ready to fold it. And we call that taco mode, but you can see the stowed optics and the sun shield's kind of on the side of it, so. We go to all these different modes, so you can bring people there to go see, that, or you can, ask for somebody to bring you into the window and stare at it. Seize that opportunity. In terms of big scale tours, which we've done before, and photo ops, which we've opened up, it's in COVID. You can't, when we did the photo of the mirror, we had people backed up, on a 3-hour line past M3, packed. We can't logistically set up a situation where that many people congregate under COVID. So we really limited the photos only to the program team, combination of people who were in the high bay, and then very spaced hours. We couldn't do it for thousands of people. And it's very unfortunate, very sad and disappointing, but it's just, it's a fact. So it'll all depend on where COVID is. I would love to be able to do a new photo op when we're in launch configuration, say in July, before we go into container and open, it up. So let's hope vaccines and herd immunity and everything else gets there.
So Scott, let me just toss in the TRA. We did do some tours last year, and we'll probably figure out something in the era of COVID of being able to get people in small groups. So we'll work on that, and we'll post something on our website or send out an email.
Scott, this is Pam again. Greg Davidson has a question. He says, is there still a possibility to get names of JWST alumni to ride on a microdot or equivalent? He says, he made promises to Adele Yates and Bill Whidden that they could go along for the ride.
Well, I asked that of NASA, and I don't, my more than hope is the answer is yes, and especially something, it would have to be something small like that. We couldn't open it up to, sign MLI like I did for advanced CHF or stuff like that on Webb, and Webb is so particular in terms of its contamination and all of that stuff. So that's, Greg, what it would be. It's something that NASA would lead. I actually asked my program manager that last week, and he himself said, let me go ask. So, yeah, I mean, what did they say? They had 11 million names that went with Perseverance to Mars in terms of how NASA had done that. I think, on some level of microdot or chip. The only thing that I've heard of with specificity, Dave and Martin, if he's on the line, Mohan, he'll appreciate his commitment to have Phil Sablehouse's name on there, the former program manager for NASA, who, it's way too early, passed away a few years ago, but as a memoriam kind of thing. But in terms of the workforce, remember, this is an international workforce, and you don't want to leave anyone out when you do it. So you have to do it in a way that scales big. So I don't know the specificity. I know I'm asking the question too, Greg.
This is Steph. Dave Vandervoort asked, with hindsight, what was the largest program risk that materialized in the last 4 years of the program, and could it have been avoided?
Yeah, I saw that question, David. Very Dave Vandervoort question. I appreciate it. And I'll give a very Scott Willoughby answer, which means a really honest one. There's a lot of things I look back and with hindsight, I would say, oh my God, I wish I did that, but I don't hold any regret on. And of course, as you know, you plan for risk and accept risk and probability and consequence. But I'll tell you the one thing that got us, and that was what also caused our longest delay in our launch slip back in 2018, was the escape we had in acoustics. And it was a case where we did have fasteners that had come apart, and mostly what I look back on of the avoidability of that is, so first, the nature of the installation of that cover assembly was that it only takes form after all of the value was added to the article, only after months of stowing sun shields and placing that out, and it has built-in springs. It's more complicated than anything, that most people can imagine, or that Popular Mechanics, wrote about us in their insulting article. We have a difficult system for everything. And what they had done is they had modified fasteners such that what you would normally do is in a fastener, the screw needs to come proud of the nut, so you've engaged it. But that coming proud of it leads to a surface that then scratches something, right? Or it creates a snag source in this insane, design. So they tried to dial in a short, fastener. And what we didn't do is qualify their implementation. We accepted the fact that the risk at the higher level assembly, we knew that we couldn't test it. We could have, but the expense of running that test early on. But we really should have vetted that risk out and looked at what we could have done at a sub-assembly mode, where we had, basically waived the standard practice and not done sufficient validation of the alternate. So that's the answer. That's really the risk. Everything else that we learned, like folding sun shields, was really hard. It took 3 times to do it. Some of the other attitude control stuff, star tracker pointing assemblies, was really hard, but those I'd say were somewhat par for the course hard. But that fastener thing got us, and absolutely, if you dial the clock back, we should have had a little foresight. And we put a lot, just so you know, Dave, assured, at least from my, commitment in the organizations, we've put a lot to improving our processes to have that rigor of how do you really validate anything that's an exception to the standard design. It has to go through extra hoops. It can't go through the same hoops on that. So I hope those blocking and tackling are more firmly in place now. Okay.
There's a question from Melissa about how are you managing battery charge during the boat transit?
So the battery, we're unpowered during the boat transit. We don't have to worry. We'll charge when we get to the launch base. So our battery, we just put in our flight battery for that Sunshield deployment. You always wait until the last minute. You run on a test battery. You keep your flight one in the fridge. And then that is now in the vehicle with its life, understood. So the biggest concern with the battery is when you're on the rocket and you switch off of umbilical and you are on vehicle power, and then you have a delay in launch, that then will limit your ability to recycle. You'll at some point in time, you'll say, oh, I'm too low on battery, sorry, stop, I won't launch for today. Hook the umbilicals back up, resolve the launch vehicle issue, recharge, start again. So that's the number one battery concern is after you get on vehicle and then you disconnect. Unpowered battery shipment won't be any issue.
So Scott, we're going to try an experiment now and just open it up for anybody that wants to say something.
Scott, it's Bob Kemmer again. Why is the shield look purple? I've never seen that color before.
I saw that pop up. That's a great question. It gets asked. So on one side, and this is where I'm going to give you the answer, and then you can't ask me another hard technical question and embarrass me, but it's silicon dope. So based on the thermal properties, we have aluminum, vacuum deposited aluminum on one side, or a silicon layer on basically a Kapton substrate on the other side. So that's basically the nature of probably some other properties, but of the silicon. And it's the alpha emissivity of that layer. So some layers we want to be more reflective, and some we want to be more absorptive, where we capture the heat and then almost waveguide vent it out to the side. So different layers have different coatings on them depending on how we want them to perform in the stack. So the pink layers are in effectively some type of silicon that's on a Mylar, a Kapton, substrate.
Thank you.
Scott, can you hear me?
That's a rare color.
Yeah, it is. As a matter of fact, for a while, sorry, just to complete on that, when it's not made anymore by DuPont, so we kind of grabbed the supply, and just slight differences in the thickness of that, I'm talking angstrom things, made it even look a little bluer in color. We didn't have to do that. And I remember thinking, well, we have pink MLI and we got blue MLI. Oh, is the telescope a boy or a girl, right? So, like we got a reveal party for Webb, but we got the pink MLI. Sorry, somebody next.
Scott, this is Dave. Can you hear me?
Yes, I can, Dave. You started this all, or we're close to it. You tell them.
I just want to thank you, and I know this is a long journey, an amazing journey, an amazing machine, and I've always been impressed with the team members that when I had it too, is how good they were and how dedicated they were, and I was so proud of the team. And I'm proud of you guys. I'm wishing you all the best. I'm going for you all the way.
That means a lot. I love your picture on the wall behind you there, and. I mean, the history of this program, somebody had asked about the history of program management. So I wasn't there. I know you were there, Martin. I don't know if there was somebody else between or before. Can you say in the, I know I picked up the baton from Martin in terms of the program, but for a long program, 3 or maybe 4. Who else was on?
I'm trying to remember who I took over. I think I took over for
Gary Rosiak, or he's typing in.
Yeah, Gary Rosiak. Yeah. I believe that's who passed it on to me. And I'm up in the proposal phase is where I was. Yeah.
Yeah, I mean, I've been on this since October of 2009. And before that, I had jobs every 3 years. I was good enough to get a new job, and then and then trouble enough to make them want to switch me into a new one. And in comm systems for 20 years. And I really, when I got the nod on Advanced CHF to be the program manager, I about fell down. I never thought, looking at the history of, you know, Dave Vandervoort and Paul Borzig and Fred Ricker, and just, I'm like, this guy, I never thought humans could do jobs like that. And, and then I realized over time, it's just, of course, it's all about the team, right? It isn't about what you can do other than leading a team. And that, you know, helped me greatly realize how to work with people, you know, that were smarter and smarter and smarter than me. So, but, you know, I don't know any other job in my life that I would have ever thought to do for 12 years, but this, I'm hoping somebody's going to give me a great job after this. I'm sure they will, but I don't know. This is it. I mean, I'm like Charlie Atkinson, right? 20 something years. People are going to spend over half of their careers on Webb. Just absolutely.
Yeah, it was just amazing sitting next to John Mather and some of these presentations and sitting there with the most brilliant minds on the planet with this stuff. And I'm just mind-boggling. That thing I'll never forget. Anyway, great job. Thank you.
Thank you.
Good luck.
Go Lion. You Penn State and Nittany Lion there?
That's right.
Lehigh, I'm the other end of the state.
Good luck to you. Oh, it's great.
Hey, Scott.
Can I ask if Martin Mohan's on the line just real quick? Hey, Fred, go ahead.
Hey, I'll say congratulations too. Just outstanding. I'm curious, after all this time of design and testing, is the system going to meet its original key requirements?
Unbelievable. The answer is yes. I mean, it's outstanding how few trades that we had to make other than, you know, at sub levels, right? Where every good system engineer doesn't allocate all their margin. They make everybody's job harder. So when they don't make it, right, you can make the system link close. But the original requirements, I mean, somebody asked a technical question that I'll give one amazing requirement, and it's our pointing stability. So when we stare at an object, you know, Hubble is complicated by a 90-minute orbit, 45 minutes, you know, sun, 45 minutes dark, and it does a lot of reacquisition, right, and collection. So it takes weeks sometimes, right, to stitch together. Webb out there at L2 doesn't have to do that, and we have a requirement to stare for 10,000 seconds and hold the actual starlight on a pixel on a backplane. So in milliarc seconds, a pixel on the near infrared camera is about 35 milliarc seconds. Our stability for a 10,000 second stare is 4 milliarc seconds. We are going to stare such that those photons hit the pixel. And there's one device with micro shutters that literally shuts off windows so you get even more contrast, right? So you take any other noise away and only open windows. The near spec has a micro shutter thing on there. I mean, that's what the Webb's going to do. I mean, we didn't have to forgive. The crowd cooler is going to get Miri down to about 6 Kelvin. That was hard. Dave Bloodgood, I know he's online. I mean, but exceptional in terms of how it's performing. So yeah, Dave, this is going to do what it said it was going to do in 2002. Hard to believe, but it is.
Hey, Scott, this is Martin.
Hey.
How you doing? Great job. Great job. Great presentation. Really, really exciting and interesting. And hey, Dave Shucks, great to see you. Good to see you.
This is a great alumni team here. Can I be a retiree one day?
You can. I highly recommend it.
I'm glad you're there. All right, who's next question?
Okay, if there's a lull in the conversation, this is Jim Cunningham. It's a totally fantastic and complex instrument. What kind of software and hardware redundancies are built in for the on-orbit what ifs?
I'll give you the biggest one that you know, it doesn't come obvious from looking at it. First and foremost, the mirrors aren't just segmented and deployable. The mirrors have motors on their back, actuators, so that we can even change the prescription. So not that we're going to have a Hubble type issue, but Webb is an adaptive optic, and that control of that software, what's called wavefront sensing and control, is actually Ball Aerospace in Boulder. Fantastic job, you know, that had the mirror contract. So that software that allows, now it's not a real-time adaptability. So ground telescopes actually get rid of atmospheric, they correct for it by a real-time actuation. So we're not that kind of adaptive, but as thermal drift or any other level of distortion occurs. So that's a huge level of redundancy. We will crisp up our prescription. I think it's planned on the order of every 2 weeks. We'll just keep fine-tuning the prescription. Every black box is redundant. So everything that, electrical, even our non-explosive actuators, which are eventually the bolt has to separate and come apart. But there's two fires, mechanisms that come into it. So the fuse can be burned by two independent paths. So, the redundancy goes through all of that. There was nothing, as much as we had a lot of mass challenges, we didn't have to cut on any of the redundancy in there. So, but it comes down to things like hinges, things, like cables and pulleys that we couldn't. So the mechanical redundancy comes, so there's actuators. And then with our attitude control, Chris Tsukamoto and our ACS team, both in software and hardware, are just geniuses. They were already building a bunch of contingency scenarios that they give, like the shimmy, fire the thrusters a little, the twirl, give it a different sun angle to, maybe let something warm up a little bit, right? If you want to see if it can come apart. So a myriad of things that we're already building into our software. So we have automated fault management for the failover. We have contingency plan software for, exactly that, whether it be a deployable. We have two incredibly time sensitive things that have to happen. One is our solar array, right? Get electricity going. And that's 30 minutes after launch, we're off the top of the upper stage and we want to get that array done. And we got about 4 hours of battery supply. We're not a geo bird. We never go through eclipse. So we don't have a big honking battery and all that mass so we can go for a long time. We have a battery to get our solar array deployed. So we get our solar array out, and then the other time critical thing is our mid-course burn. After we get off the upper stage, we burn our own rockets to get out to L2. And that it's time critical in that the longer we wait for the ideal window, the more fuel we'd have to burn, therefore the less fuel we'd have, right, for mission life. So we really want to hit that burn within a few hour window. So not time critical a second, right, or oh my gosh, I miss it. So those two critical things are the things, of course, you're going to be ready for. And then even say a solar array didn't come out, can we orient and get at least the outer panel getting sun, right? Getting a little electricity. I mean, it's things, the geniuses that we work with have spent this time. It has not gone to waste, taking longer on the ground. You just use that, time to prepare more, right?
Great. Hey, Scott, there was one thing that used to worry me a lot, and you're right.
And then
most of the things. Sorry.
And then you left.
Yes. Most of the things that we have from a fault management perspective on the satellite are pretty benign. The one that always worried me was once we get into orbit, into the transfer orbit, and start deploying the sun shield, those mirrors then go into shade and they will never see sun again for 10 years. That's how you get those mirrors to 40 and 50 Kelvin. So the guidance and control that keeps that mirror in the shade, it can't screw up. And that's one of the things that always worried me is if you illuminate something at 40 Kelvin in direct sunlight, we don't know what would happen because we know it's bad.
It is absolutely a big concern when we get off the upper stage and we're on our own before the sun shield comes out. And even when the sun shield comes out, we have our sight lines, exactly that, because the mirrors, but also the composite structure that holds the mirrors, the T sub G of the glue, the glassification temperature when it goes from, holding it to where it, softens is definitely one of those things. Exactly. Our ability to hold spot and attitude control is critical. But go Chris Tsukamoto.
Scott, I have a question.
Hey.
I go back all the way to the original Hubble launch when we were absolutely flipped out by the level of national attention we got before we launched the thing. like first front page of New York Times in color picture ever. Are you guys prepared if at the end of a couple of really grim years, this sort of demonstration of something positive and successful, you know, blows your wildest expectations?
I don't know. I've hit both rails of joy and sorrow that, you know, from a programmatic, of course, with the fastener issue and having Wes testify to the success. But I'll tell you, I woke up 2 weeks ago, folks. If you haven't seen it, you got to just go New York Times, James Webb, and you'll see a piece by Dennis Overby 2 weeks ago that was just exceptional. I mean, he's ready to launch again. I don't care about a snarky comment. I got it. Like I said, I'm proud this thing is hard. I'm not shy or bashful about this. This is, you know, something that I'm not saying I'm glad it took longer, but is just, like I said, emblematic of it. But yeah, this whole team, what we've tried to do though, by living in daylight, is almost prepare ourselves, and we live with the joy. I mean, if you celebrate too early, I don't say we've ever spiked the ball on the 5, but, you know, celebrating a success was initially thought to be hard. I mean, you know, it was really hard. I remember, you know, when Martin was back there, just because the program was always struggling with annual funding. I mean, I got twice as much money as Martin ever got, right, in a fiscal year. But, you know, you almost didn't want to celebrate success because you knew something else wasn't going to work. And people were like, how can you say that's good if this isn't? We started celebrating success loudly, right? You know, when we did things. And let the team enjoy that, because, I mean, talk about this marathon. How do you keep engineers engaged, you know, on 10-year, 20-year, you know, journeys? I wanted them to feel something they could bring home and share with their family, right? So, yeah, I don't know how ready. Thank you. I appreciate, you know, that. But just waking up 2 weeks ago and seeing a note from Omar, my PR person, saying, "Did you see the Times article?" I'm like, whoa. And I'm like, and then pictures. Amy Lowe is going to be on a panel. We have a new movie coming out, The Hunt for Planet B. It's going to be released at South by Southwest. And when I say we, this one's more about the search for life. Webb will be a part of it, but there's several Webb engineers in there. I got a little cameo spot, and Amy Lowe is in there, and John Arenberg is in there. So anyway, that'll be coming out in March. I don't know when it releases. It goes through the film festival cycle.
Hey, Scott.
Greg Sarasevich, just want to say hi. I just saw his note there. So.
Hey, Scott.
I can hear
you. You can hear me? Okay. This is my first Zoom meeting, so forgive me.
Please identify yourself.
Yes. I was wondering what kind of show we're going to get when you're traveling out to Lagrange Point. What kind of video we got on the deployments, and also when do we expect first flight?
Good. 2 things I didn't say. So yeah, let me keep filling in this grand picture. We do not have cameras on board. I don't know if Reggie was a part of one of the many trades. It's really complicated because if you put a camera on Webb on the optics side, it's a conductor. So to run your optics at 40 Kelvin and then put another, you know, cameras, and because it's on the shady side, lighting and all that stuff. So and then you need more slices in your solid state recorder. It's really hard. If we, you know, even if we had done it on day 1, but we looked at doing it, you know, 8 years into the design. So what we will get is telemetry and video, but it's very much what they were showing with Perseverance. So if you go look, and it was exciting. I mean, there were control center people with telemetry telling them, the parachute's going. I can see that the speed is slowing. Where my comlink had the, you know, the bypass of the transfer stage. They could tell a dip in their comm when it passed through the RF window. So it'll be that type of animated, you know, go through, and then here's what's happening as telemetry convinces us. And we're a little bit more real time, right? They had an 11-ish minute lag, you know, depending if they, you know, they had to stop going direct, and then I think through MRO, right, and then back from Mars. You know, even 1 million miles away is still reasonably fast enough, you know, at the speed of light. So, you know, we're, you know, round trip, we're less than a minute delay, but, you know, so in that regard, we'll kind of really know what's happening via animation. And I'm sorry, what was the second part of your question? It was
when do we expect first flight?
Yeah, so I mentioned it's 29 days to get to Lagrange 2. It's 5 more months to calibrate the telescope. It's 2 to 3 months just to let the parasitic heat that this thing leaves Earth with to get out and bleed to all of the mirrored interfaces and the radiator panels and get out of there. So a lot of it is, so there's mirror cooling, and then at some point in time, we'll actually get 18 images. Each of the 18 mirrors will kind of catch something, but they won't be phased. And then eventually the 18 will come in and create an image, and then, you know, that image will get crisp up. Our requirement is to turn over the keys to the scientists 6 months after launch. So it does take a long time. The super sweaty time is those first 2 weeks, but it is a half a year for commissioning. Now there'll be first light moments, I'd say around month 4 or 5, but I don't know what NASA will do with the baby pictures. I don't know what they'll do with phasing pictures as opposed to I don't know, a crisp image.
We'll have to be patient.
Yeah.
Thank you very much.
Scott, in answer to your question, I was there when, I'm sure we talked about cameras throughout the life of the program, but when I was there, we were talking about cameras, but it was right at the height of the weight problem, the mass problem.
Yeah, too much mass.
So adding stuff on just didn't seem like the right thing at the time. But there's a cute story that I heard. John Ehrenberg is the guy that does, he's sort of the next to Scott, the face of JWST. He's given more talks about JWST than anyone except for Scott. And so I went up to John once and asked him what the best question he ever got was. And his answer was a high school kid student asked him, well, when I see these depictions of the telescope, why can I see them? How can I see the mirrors? Because in fact, once you deploy the sun shield, the mirrors are going to be black. You won't see. So we'd have to put lights on. But that was really a good question.
That's a pretty insightful question for a high school kid.
Yeah. So the answer, of course, is artistic license. But if you had cameras after the deployment of the sun shield, you wouldn't see anything.
Yep.
Not on the interesting side, anyway.
Yeah.
Yeah. This is Joe Scafidi here. I was instrumental in one of the first trade-offs where NASA was asking for cameras. And the big stumbling block that I ran into was the lighting. Couldn't get enough lighting to make putting cameras on useful. And so we let that one go for about a year, and then we did another look at it, and I walked away from that thing scratching my head, and it's 11 years later, and I still can't figure out how to get the wiring, the lighting for those cameras.
Well, thanks for adding to that, Joe. You're right, and so we'll work with via telemetry and animation. So how's it looking, Reggie?
Yeah, I think
I've got one question. This is Scott Minium.
Hey, Scott, another former boss.
Who builds the comm links?
So the comm comes through a lot of suppliers. So the S-band is Thales Alenia. So the TNC is Thales Alenia, Italy. We're working actually with a transponder thing now. The Ka band equipment, which is the data, the higher data rate. The tubes are TSAT. The dish is RUAG. So it's TRW Northrop creating a comm subsystem, mostly from vendors and interesting enough, mostly from foreign vendors. So it's our comlink, procuring through. And of course, the comlink, well, not of course, but so from a TNC, it's about talking to the Deep Space Network, except a little harder, right? Because it's out Lagrange point 2 as opposed to, there, but not, that's what they're doing anyway, right? So the S-band telemetry and all of that had a lot of already industry play because, those companies were already building equipment that could talk down to, to NASA's DSN. So it's a myriad of players, that we built up into a subsystem with our comm engineers.
So Scott, thanks for your time. I hope you've been watching the chat. You've been getting a lot of comments about people really appreciative of what you've done here today. So we appreciate it.
I do. I hope you can screen capture the chat. I'm trying to read them all now before I hang up on this.
No, well, we're going to capture the chat.
I did. I just saved it. So.
Okay.
Oh, that's awesome.
All right.
I like the reference back to Kennedy. We don't do these things because they're easy. We do them because they're hard. No truer statement, than with Webb, for sure.
Good luck.
Hey, Lenny. Yes, the supply chain team did great. Truthfully, I mean, I went from 20 years in comm where we were 85 to 90% vertically integrated to Webb, which was about half supply chain when I took it over. A very different world for me with having at that time ATK, Kodak through 5 name changes, and Ball, not to mention Nexov and the others. So it was a whole different world to, manage that in a very critically important function. I know there was a lot of folks I saw that were signed up for this, whether on Rich Capter and Mahendra Patel and some others that, very, very thankful for. Mike Bilali. Anyway, I hate to say names because then I forget to say all the other names. So
Yeah, don't worry about that.
I'm getting old too.
Great talk. Thank you.
Okay.
And in answer to your question earlier, Scott, we'll save a membership in TRA for you. So
thank you. Give me my first year free.
Yeah, well, everybody does, Scott, but for you, we'll give you an extra year. We'll give you an extra year.
You'll remember. No.
I'll remember. Scott doesn't forget things like that.
No, that's a curse and a blessing. Well, thank you, everybody. This is really, it was my privilege to share and let people know things that you worked on. And I'm just a lucky person to be here, at the end of this stuff, a long journey to get to it, but it's real. So, I mean, this is our year. It is wonderfully exciting.
Scott.
Thanks for taking us across the finish line.
Scott, talking
Yes.
about membership in TRA, one of our biggest difficulties is getting known to people who are retiring. So please talk up TRA and let people know we exist.
I will. I'm going to send a note to Gus and Bruce Mallinger to asking them why they didn't show up for my talk.
Yeah,
There you go. That's a good start.
Yuri
Yeah.
too, yeah. Thanks to everybody who joined us. And just a reminder that if you have ideas for other Zoom type sessions like that we can do that you would enjoy and reach a large audience, please let us know.
Nice job.
Yeah, great. Thank you so much, Scott. That was wonderful.
Thank you, everybody. Wish I could have saw you in person.
Yeah.